If most of you have used Blackboard chemistry before, and so you're used to making things into a single PDF, there's a couple of you who are brand new to doing this as an online class. And so if you don't know how to submit as a single PDF, please make sure you talk to me. I probably wrote a note to you, and I've caught some of you. And the other thing is, and I'll mention this more tomorrow, or I'll mention it again tomorrow. This week I'm planning to I'll be here, I'll be here at 1, and if anybody's here, I'll stay and do an office hour. And if more for the evening people, so we'll say 1 to 2. I can say a little bit longer too, and then I'll come back on at 5. For anywhere from 10 minutes to an hour. So if you want me to stay here, be here like in those first 10 minutes. So I stay on. I'm not going to sit on Zoom for an hour waiting for people. I'm doing that because I got to go through the first set of worksheets, and people either got like a 6 or they didn't. And so if you didn't get a 6, I would recommend finding the time, which we actually keep moving on. So you kind of have to keep moving on with me, and then take a deep breath and say, I'm going to have to change how I'm doing this, and finding the time when I'm here. So on Friday, and saying, okay, I want to go back. And redo my first worksheet and stuff. So I wrote a note to some of you. So if your score was not as high as you wanted, also if you answered that original email, added the bonus point. So a lot of you got 7s on that worksheet. So do the bonuses. There's bonuses on the labs. And also the labs due on Fridays. So if you want me to look at the lab, but you can do that. But we're moving on today to acids and bases. Just a couple things. So what do you know about acids and bases? Like when you hear we're doing this topic, what comes to mind?
Together they make salt.
Right. Okay. What else? Say that again.
The pH is lower than 7 and pH is higher than 7.
Yeah, so for acids, most people think of pH. So pH is below 7 for acids, and pH is above 7 for bases. There's a video I'll be posting for the lab for next week, and I talk some about the history of some of this stuff, but I did not actually know this until about 5 years ago. It was actually this day when I was teaching this. I love Google Doodles, and it was like a chemistry Google Doodle, and it was of the guy who came up with the pH scale, which was only like 120 years ago. And it blew me away, because I was like, I just kind of took it for granted that pH has been always around as long as humans have been around, but of course it hasn't. Somebody came up with a concept, and we'll get to pH. So pH below 7 is something that is acidic, and a pH above 7. And as I think it was Elizabeth said, when you miss an acid and base, they become what we say is neutral, or they become a salt, and that is typically a pH of 7. That is assuming that the moles are equal, that you have a perfect equal amount. There's also another assumption beyond that, and we're going to get to that today, because it would assume that the strength of the acid and base, they perfectly neutralize each other. We'll actually see that more next week when we get into titrations. Anybody else? What do you think of when you think of acids, bases?
Acids are sour.
Yeah, and that's actually what the word acid means. So acid comes from, I think it's Greek, acidus, and the word acidus means sour. So whenever, that's why the lemon guy is there, whenever you have anything that's sour, it is an acid. So in our house, our fruits, so lemons or vinegar. So yeah, that reminds me, you guys have started your healthy change. You had to start today if you hadn't already, for 7 days or for the whole 30 days. So lemon, vinegar, those are things that are acid. So with that, does anybody know what bases taste like? There's actually 2 answers here. So the original term for base was actually alkali. So whenever you see that prefix AL, it's actually saying it's an Arabic word. And so it was, so like algebra. So Kali is, sorry, for potassium. And so most of our bases is, if we took, right, we think of potassium hydroxide. So potashes was where potassium came from, but they had this idea here. Anybody know a common base? Or go ahead. Baking soda, or my picture here is soap. So most of our cleaning substances, so anything that you're using to clean, except for vinegar, vinegar is definitely an acid, but soaps are going to be bases. And so this is where I always joke, how many of you know what soap tastes like? I personally don't, because I did not have to have my mouth cleaned out as a child. Probably, maybe you guys weren't this brutal in Egypt major, so you never had to put soap in your mouth. But that's the joke in this country, that if a kid says a bad word, he has to put soap in his mouth. So a soapy taste. So soaps are going to be bases. But the other thing, the real taste of them is bitter. And I mention that because we all actually have this bitter addiction kind of. Bitter is usually telling you have a poison, but bitters also, a lot of us have a attraction to it, because a lot of you love coffee. I've been having a coffee every morning, and I love chocolate because of the bitterness. And it is the alkali in there. And it is more specifically a certain element that is making it bitter. Does anybody know what element is in a lot of these?
Theobromine?
Well, theobromine is the molecule that is the wonder molecule in chocolate. The element is nitrogen, and we're going to see why when we get down here, that if we see nitrogen, we're going to usually, as soon as you see nitrogen, you're going to be thinking, hey, that must be a base. There's a few exceptions in there. But usually when most people think of acid or base, they're not thinking of a certain element. For acids, we usually do, and the element we're thinking of for acids is hydrogen, but not actually the element hydrogen, the ion. So hydrogen ion is what we found out acids have in common. And the thing that makes it special, why hydrogen ion is special, is 99.99% of hydrogen has 0 neutrons. So remember when we put the mass number and the atomic number come out the same for hydrogen. And if it has a +1, it has 0 electrons, which means this hydrogen ion isn't actually an element anymore. It's a subatomic particle. It is just a proton. So a hydrogen ion is really a proton. They may know what ion we think of, most people think of when they think of a base. Starts with O, ends with H.
Hydroxide?
Yeah, that was good. You got the hint. So most people think of hydroxide. And again, the video I made for the lab for next week, I go through, there's some classic definitions of acids and bases. So the original definition from 120 years ago was that acids produce hydrogen ion and bases produce hydroxide ion. There's a huge extra piece to that definition, and that is that we have to be in water. So to get the hydroxide, it's in water. Acids don't actually ionize. It is the water actually pulls the hydrogen off the acid. But acids do, we're going to see, have this hydrogen ion. That definition became refined once we learned about subatomic particles. And so the definition that is more scientific used is that acids donate protons. And if we're looking at it in terms of protons, if an acid donates a proton, then we would say a base is a proton acceptor. So this definition, again, had to come out once we had the idea of subatomic particles, and it also probably came out about the time when oxidation reduction came out. So if you remember when you learned, we're going to come to oxidation reduction in a couple of weeks again, but oxidation reduction was gaining and losing electrons. Well, we're going to be looking at this for acids and bases in terms of donating or losing a proton, a hydrogen ion, and gaining a proton or gaining a hydrogen ion. So that's another way of saying a proton acceptor is that they gain a hydrogen ion. And we're going to be doing chemical reactions in about a half hour, and that's what we'll be looking at. There are other definitions, and we'll get to that probably tomorrow in the notes. Let's see. With that, our common acids, there's really two main categories of acids. We have inorganic and we have organic. So for a chemist, when we say the word, if you go to the store and you say the word organic, or you say to a farmer, like Damon grew up on a farm, organic, the thing you think of is, oh, we're growing it without all the chemical compounds and stuff. But the term organic actually comes from chemistry, and organic means that it's carbon based. So we're going to have carbons and hydrogens when we're talking about organic acids. And let me finish my definition. The X and the Y just mean the number of carbons and hydrogens is not important at this point. But to be an organic acid, it's then going to have a CO2H. This is the piece that makes it an acid. So the number of carbons and hydrogens, and then you're going to see CO2H. The hydrogens that are attached to carbon, these are nonpolar. So if you remember back when you learned in Chem 222 about polar and nonpolar, carbons and hydrogens don't pull on each other. And so you're not going to be able to pull a hydrogen off a carbon. So you're not going to donate a proton that's attached to a carbon. This hydrogen here, that's the one that's going to get donated. And the reason for that is, we'll just write it like this. This is more for your information, and I would assume, because it's how it usually is about half of you are going to move on to organic chemistry, and you'll run into this, so you'll be grateful. It is these double oxygens attached to this carbon, and what do you remember from your 221 or 222 experience about oxygens? When you think of oxygen, periodic table, it's up there in this
Grading.
it's in this corner that wants its own electrons, right? And so go back here. The oxygens are pulling the electrons, and a bond is electrons, right? What's holding the oxygen, the hydrogen to the oxygen, is electrons. And so what happens, because the oxygens are pulling the electrons, it's really easy for that hydrogen to pop off. And when it pops off, it doesn't take any electrons with it because the oxygen holds on to it. And that's our definition of an acid, is a hydrogen with no electrons. And so it's this double oxygen. One oxygen doesn't do it. It's this double oxygen thing that makes it an acid. Inorganic acids, you're going to see something like, let's do it in red. That was the definition nobody gave there. Something like HCl. So you're going to see a hydrogen with a nonmetal. So you're going to see a hydrogen plus a nonmetal. So something like HCl or H3PO4. Or inorganic. So we don't deal with the carbon. We show the hydrogen first. Organic chemistry and biochemistry, we show it after the CO2 part. So it's just something you have to look for, and we'll do practice with that today and tomorrow, and you'll get used to it. And here, this hydrogen is just going to pop off. Before I forget, there was one other piece I wanted to mention, and I talk about this in the video. So the video is kind of meant as a visual to help with some of these definitions. Is another definition. somebody usually mentions has to do with litmus paper. So litmus paper, you've probably all heard of it, is there's all different types of pH indicators. And so litmus is actually from lichen, which grows on all our trees all over here. Acids turn litmus red. Oops, that's purple. So not all indicators are going to turn red, and bases turn litmus blue. So you can see a wonderful poem there, right? Acids are red, bases are blue, blah, 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 blah. That's like my level of poetry. Yeah, every indicator is different, but litmus is by far the most common one that everybody's heard of. And that's why I wore pink and blue today. You can hardly see any of me, but trust me. All right. Organic, this page is a lot of definitions, a lot of wordy stuff that we have to go through, and then we'll get to the math. So kind of bear with it. As far as bases, if we have inorganic bases, there's two types that you're going to look for. And again, sometimes I say alkali. I usually say the word base because it's easier to pronounce. You're going to see a metal hydroxide. So NaOH would be an example. The other big inorganic base, there's actually many, but really the only ones we're going to see are those or NH3. So as I mentioned, you see nitrogen, you're thinking of base. So ammonia, NH3 is ammonia. Ammonium is something different, and we'll get to that on the next page. As far as organic bases, so again, organic means we're going to see carbons and hydrogens. The number of carbons and hydrogens isn't important, but you're going to see nitrogen. And the reason for this is on your periodic table, nitrogen needs 3 electrons, right? 3 bonds. So nitrogen is usually making 3 bonds to get to its octet. And so it always has this lone pair of electrons there. And that lone pair of electrons is going to attract that hydrogen that has no electrons. And so that's why nitrogen loves to act as a base. So when you see nitrogen, so all those bitter substances we love to drink and eat, they have carbons, hydrogens, and then they have a nitrogen. They usually have multiple nitrogens. And so when you see the nitrogen, think base. Remember that. So when we get to the next page, we're going to be writing chemical equations. And one of the first things you have to do is identify the acid and base. So as soon as you see nitrogen, you'll say base. That's my base. So the other one must be the acid. All right. Some more definitions. Just keep going unless somebody has a question. We're going to look at monoprotic. So protic means protons. Mono means 1. So this is 1 hydrogen. Acid means donating. So 1 hydrogen to donate. It's really simple. And poly means more than 1. So 2 or more protons, hydrogen ion to donate. The vast majority of acids are monoprotic. So what would be an example of a monoprotic? I gave them up above. Right there. HCl. I'm so glad you said that. All right, so HCl would be a monoprotic. My organic one here, this is also a monoprotic because it's only this hydrogen that's coming off. Even though there were other hydrogens, those hydrogens can't be pulled off. Something that's polyprotic would be like our phosphoric acid, H3PO4. So it has multiple ones. There are many polyprotic organic acids, but they would have to have multiple of these CO2H groups. And so citric acid which we think of for vitamin C. No, ascorbic acid. Anyway, both of those, citric acid has 3 CO2H groups. And so it's a polyprotic. All right, now the next one is amphiprotic. We'll go with green for the frog. I'm laughing because I always give this example with the frog. And then I ask at some point, like on a worksheet, and everybody like is obsessed with the frog. And the frog has nothing to do with acids or bases. It has to do with the end of times in the Old Testament or something when the frogs infiltrate Egypt, which is just so fun to imagine. But the prefix amphi means basically either or. So amphibians, which are frogs, they are born in the water as tadpoles, and then they live on land. So they're amphibians. People who are ambidextrous, they can write with their left or their right hand. So amphi means both. So amphiprotic means it's something that is both an acid and a base. Some places actually say instead of amphiprotics, they say amphoteric. So they mean the same thing. So it just means it can accept or donate. The number one example of an amphiprotic species is water. Water can act as an acid or base. Now, that blows most students at this point because they're like, water's neutral. It's not an acid or base. Actually, it is. It's both. It depends on what you mix it with. And we're going to do a whole bunch of equations on the next page for next 2 days. And so it's going to change your perspective. So if we add water, let's say with HCl. So if we mix the water with the HCl is definitely the acid. So I'll just label it as A. This hydrogen is going to be donated to the water. And so the water is accepting the hydrogen, and so we call the water the base. You can use whatever colors you like, and we'll show our reaction. So the water has picked up a hydrogen. It is now H3O positive. And I asked this question 2 days ago, and somebody got it. Does anybody remember? And this, you're all going to know this by the end of today. What is the name of that ion? Major's the one who got it because he had me.
Hydronium.
This is hydronium. So, the big myth out there, you don't actually get protons. This definition is not correct. Most people, when they show acids, they say HCl becomes hydrogen and chloride. But to be hydrogen, it would be a proton. Where are the protons in your atoms? Go back to that lesson you learned about atoms, right? That atoms are 99.9999999999999. It keeps going. They keep adding more nines. It's like an infinite number of nines, emptiness. You and I are empty. And then there's that very little center of the atom. Every atom is where all the mass is, and that's where the protons are. So they have this ginormous empty castle around them, and suddenly they don't. They're never like that. And so the water pulls the hydrogen off. The hydrogen's never by itself. It's bound to the water. So we're not going to talk about as hydrogen ion. You're going to see me talk about it as hydronium. And the other pieces we get Cl negative. All right. So in this case, water was acting as the base because it picked up the extra proton, the extra hydrogen. In our second example here, just to show you amphiprotic, is water with NH3. The other quick comment for you is there's only so much I can cover in class. The study set, I'm pretty sure the first page of the study set is bunches of examples and stuff. And so some of the examples we're going to see with the study sets. When you do the study set, just try the best you can. And then as we go over it tomorrow, realize you're going to be filling in. Ideally, you're going to fill in extra notes and stuff. But in this case, NH3 is a base. And so the water is going to give up the hydrogen. The water must be the acid. An acid does not react with another acid. A base does not react with a base. Acids and bases react with each other. So in this case, water is going to give up one hydrogen, and we're going to end up with OH negative. So the water lost the hydrogen, and that is, of course, hydroxide. And the NH3 is going to pick up the hydrogen, and so it's going to become NH4 positive. Yeah, we're going to add to these equations, and there is, how I showed it is correct. If you notice, this one has one arrow, and this one has two arrows. That's actually really important, and I'm going to get to that. There's a lot of details here, but that's just an example of what amphiprotic, that the water can act as an acid or base depending on what it's mixed with. So again, an acid it doesn't just ionize, it has to be in something that pulls the hydrogen off, and so the water has to be what pulls it off. And the same with a base. A base is that it is gaining that hydrogen. Another example of amphiprotic, is Damon mentioned this when I asked for examples of bases, and he said bicarbonate, like sodium, baking soda. So baking soda is sodium bicarbonate, but HCO3 can act as an acid or base. And again, when we do the equations on the next page, and also tomorrow, you'll start seeing this. And over all of next week, we pretty much just work with acids and bases. So there's the hydrogen. It can donate that hydrogen. It's really hard for it to do that, but it can. So it could donate. And that negative sign, that means it could accept. It has space for a hydrogen ion. And so there it can accept. So it also is something that could act as an acid or base. How do we know what it's going to be? It depends on what you mix it with. If we mix it with HCl, HCl is the acid. HCl is going to always be an acid because there's no place for it to pick up anything. If we mix it with NH3, NH3 is going to want to pull that hydrogen off. So it depends on what we mix it with, and we'll get to that. There are a few other examples of the amphiprotic, but we'll leave it like that for now. Let's go through these other definitions. The conjugate acid, conjugate base, you're all going to have it after we get through the next page. So just write a note right now. The key is this: they differ by only one proton. So nice that I wrote that there. And you're going to see me abbreviate it as Ca for conjugate acid, and for conjugate base, I just say Cb. So what it is, every acid has a conjugate base, every base has a conjugate acid. So acids have a conjugate base, and that is what they differ by one proton. So an example would be, let's actually do this guy up here. H3PO4 is our acid. Its conjugate base is one hydrogen different. So it would be H2PO4. And now it would have a negative because it lost the hydrogen. So that would be an example of an acid and its conjugate base. They differ by one hydrogen. They're partners. So in the chemical reaction, we start with the acid and base, and we end up with the conjugate acid, conjugate base. An example of a base with its conjugate acid, just a simple one, would be, let's take NH3 because it's simple. And a conjugate acid means a base is going to accept a hydrogen, so it's going to become NH4. Now, the biggest issue students seem to have with this is my plus and minus signs. If you gain a hydrogen is a positive. When you gain a hydrogen, you're going to go up by 1 charge. When you lose a hydrogen, you lose a charge. The reason it drives students crazy is because you've been trained to do everything with electrons. Everything's about the electrons, except when we're doing acids and bases, which is what we're doing for the next 2 weeks. You'll be fine. We'll get to that. All right, so that's the idea of an acid conjugate base or base conjugate acid, and we'll see it on the next page. All right, last thing, because this is key for the next page. Strong acids, you're going to see me just say SA for strong acid. A strong acid means it completely dissociates. So it completely dissociates. Again, the term ionize is incorrect because acids don't ionize. They have to have something pull them apart. So it completely dissociates or donates, which means it's a one-way reaction. This is why we couldn't do acids and bases until now, because there's only 6 strong acids. Almost everything, the other quadrillion acids, are weak acids. So Wa means weak acid. And based on everything you've learned for the past 48 hours and 30 minutes, what must be the definition of a weak acid? Well, it's going to be a two-way reaction. What equilibrium means is you only have partial. The reaction's not complete. It's a partial reaction. So it's a partial dissociation. I guess we have to say partially dissociate. So it's going to be a two-way. And again, those are just the abbreviation for strong and weak is Sa and Wa. Everybody pretty much uses that. All right, almost all the acids are weak. There are 6 strong acids. This is where you can tell how long teachers have been teaching. Dr. Russell goes with this too. If you go on the internet, they don't agree with me anymore. And for our purposes of our class, we're just going to go with these classic 6 and not make it a big deal. If you end up going and becoming an environmental cleanup person, whatever they wanted to find, there's a couple other ones they now say are strong acids because they're really, really strong weak acids. But the classic 6 are HCl, HBr, HI. And that's why I'm doing green. HNO3, so nitric acid. Nobody debates that these guys are strong. H2SO4. So what's in your car battery? H2SO4 is a strong acid. That's why these guys are donating all their hydrogens. When we write our reactions, like up here, that's why this was a one-way reaction. And the strongest of them all is actually HClO4. Anybody remember the name of this one, the last one that I wrote? What would be the name of that?
Perchloric acid.
It is perchloric acid. I don't know who said that.
Was fun.
That's awesome. You learned your nomenclature. It's funny because in previous years, everybody like knew it, but because we're like in this environment where you guys have notes, not everybody knows all their pieces as sharp as in the past. Tomorrow I'll talk about why the oxygens, I kind of already did. Having those 4 oxygens really makes it pull, and so it's really easy to pull that hydrogen off. Now, there are strong bases. Anybody want to take a guess what the label for strong base is going to be? SB. And then weak base is WB. So there are 6 strong bases. Nobody memorizes them. There's a list somewhere. We're not going to worry about them. The only strong base we're going to worry about is going to be something like NaOH or KOH. So the hydroxides. And that just becomes important for something we do. There are actually 6 strong bases, And I do know the list, but we're not going to muck it up because they're so uncommon. And so unless you're specifically working industrially with one of them, so you could see if you were somebody who was the cleanup person, if there's a spill of a strong acid, you take it. I mean, any acids we take seriously, but a strong acid is going to really burn you. If we were in lab and you got a strong acid on you, you're not going to be like, oh, I spilled some acid on me. You're going to be at the sink rinsing it off. But the cleanup can be different. In all honesty, in lab, we had a huge garbage can filled with baking soda. And so pretty much anything that's spilled on the bench, I would just say pour some baking soda on it, and because it's gonna react with acids and bases and make it that we can clean it depending. Yeah. All right. Right. And don't be like Johnny. Because yeah. All right. Never, ever eat or drink in the lab. All right, we're going to do some reactions. So I apparently have space up here because I usually talk about something. We're going to fill in that space as I go along. And I think the first thing is that you're going to label your acid and base, which are your reactants. I'm going to be giving you your reactants. If you remember back to your 221, you guys did double displacement reactions. That's pretty much what we're doing here, except there's an exception. When you did the double displacements, we assumed everything went to completion. Everything was one way, and we're not doing that anymore. And the other thing is, once we label them, the acid only donates one hydrogen. So we're not going to have to deal with balancing. Everything's going to be coefficients of 1. So we're only ever going to give up 1 hydrogen. So even here with the H2SO4, even though it has 2, we're only going to give up 1. The second hydrogen's the second reaction step, and we'll get there like tomorrow or eventually. All right, H2SO4. Like first thing you want to say is which is the acid, which is the base. So NH3, right? We see nitrogen, that's a base. H2SO4, you want to label it more than just A. It is one of the, I should have written them on the board behind me. You guys want to make a little note card and write these 6 on there. And usually it's on the board behind me, but that would require me to stop for a moment. H2SO4 is a strong acid. So if you see a strong acid, label it like that. Why? Because of this next step, we're going to do the reaction, which means 1 arrow. If you have a strong acid, you do 1 arrow. On the next one, there's no strong acid. So we would do 2 arrows. So if you see a strong acid, it's 1 arrow. Weak acid, it's 2 arrows. So you can put a note of that. Strong acid, 1 way. If it's a weak acid, if it's not as strong, pretty much. Again, there's 6 strong classically, and there's a couple of chloric acid is one that sometimes, I can't think what the other one, that sometimes creeps in there. All right. Now, as I'm teaching, I'm going to show you a specific way. It just helps me to visually show you. I have noticed the students who do it this way tend to always get it right. And then students are like, oh, that's like so cheesy. They end up doing random stuff. I like to circle the hydrogen on my acid and show that it's going to go over there to the base. So real quick, the acid is not always the first one. It could be base plus acid. It just happens to be on this example, we have a strong acid plus base. All right, so what we're going to end up with, 1 hydrogen. So it becomes HSO4 negative because it gave up 1 hydrogen. So my question is that a conjugate acid or the conjugate base. They always, it's like yin and yang. An acid does not become an acid. The acid gave up a hydrogen, so now it's the conjugate base. So the acid always becomes its opposite. So the acid becomes the conjugate base. The NH3 is going to gain a hydrogen, so it becomes NH4 positive, and so it is the conjugate acid. And we're done. The hardest thing students have, one is, this is easier than double displacements because we just always move one hydrogen. There is always a change of the charge. So gives up a hydrogen, came negative, it gains a hydrogen, it becomes positive. All right, let's do the next one. This is a weak acid. You can write Wa if you want. Some students do, or just it's not as strong. This is going to be my hydrogen. This is the organic acid, the CO2H. So this is the hydrogen that's going to move over to the base. That's actually why I do it this way, to emphasize. Again, why these hydrogens here attached to the carbon, why do they not move?
Does it have to do with the octet?
It has to do, no, they all have an octet, except hydrogen. Has to do with what type of bond it is. What type of bond is it?
Right? Bond?
It's nonpolar. It's a nonpolar, which means it's sharing equally. So there's no pooling. The electrons are nicely distributed between the carbon and hydrogen. You need an extremely polar bond, which we have with OHs. Remember NOF? So those H bonds, those guys, right? So this hydrogen gives up to there. So we're going to end up with CH3, CO2, negative. Is that the conjugate acid or the conjugate base?
Conjugate base.
It is, because we had the acid becomes the conjugate base. And the water gains a hydrogen, so H3O positive is the conjugate acid. All right, so we're gonna go, let's go this far for today. I'm gonna pause, give you a moment to try those two, or you can take like a 2-minute break. All right, I'm back. So on the next one, you never label the water first, because water is just whatever it needs to be. The water could be the acid or the base. So you look at the other one and you see the nitrogen. And this is the one thing you get from today, that you see nitrogen, you think base. So nitrogen's the base, that means that water is the acid. So the hydrogen of the water is going to the base. It goes to the nitrogen. The carbon, this is actually would be the answer somebody like anticipated my next question. The carbon can't pick up any more hydrogens. It's already got its maximum octet. The nitrogen can. And again, it has to do with how nitrogen is. It's got that lone pair of electrons. So nitrogen makes 3 bonds and it has a lone pair, so it has room to add another one. Carbon makes 4 bonds, and so it doesn't have room for anything else. I want to take a moment to point out something. I said when you see nitrogen, think base. There is always an exception because it's chemistry. And that is here. And this one is the acid because it has that positive. So when nitrogens are neutral, like they are over here, when there's no charge, then of course they're going to act as a base. But if something suddenly has a charge, when it's an ion, the rules change. And we're going to talk more about ions tomorrow. So, all right, so the hydrogen goes to the nitrogen because the nitrogen can pick it up. 2 arrows, because I don't see a strong. and C6H5, we'd say NH3 positive. So the nitrogen here, it goes to NH3, not NH4. Why is this one NH3 with a positive and that was NH4 with a positive? We're not drawing out the Lewis structures, but this nitrogen is attached to this carbon piece here. This nitrogen just is going to be surrounded by 4 hydrogens, but because this has this extra piece, then it only has room for those 3. So it's like here, there's this carbon piece, which is the C6H5, actually a benzene ring. Which if you take organic chemistry, you'll see that like right off. But it has to do with the octet that somebody had mentioned. So just go with it. The hydrogen, it always changes by 1, and you have to show the hydrogen on the nitrogen. So you would show it after the nitrogen. And then the water becomes hydroxide. All right, is the hydroxide the conjugate acid or the conjugate base?
Conjugate base.
Yes. So the water acid becomes conjugate base, and our pyridinium guy is going to be our conjugate acid, or anilinium. All right, next one. These purple. They both have hydrogen. They can't both be acid. Which one is the acid and why?
HI, because it's a strong acid.
Yeah, the strong acid's going to win. You're not going to see 2 strong acids. I mean, there's probably somewhere online somebody asked that. The other reason the high is it's a strong acid, means one-way reaction. The other thing is this guy is amphiprotic. It has a hydrogen. So if it was mixed with something like our nitrogen compound here, it would donate its hydrogen to the nitrogen. But it has a -2, which means it does have room to accept that hydrogen. In this case, it's inorganic. We'll show the hydrogen when we pick it up in the front. So the charge this had 1 hydrogen, now it has 2. It had a -2, so now it's a -1. So you can ponder your charges, and then the high just becomes I, and it has a -1. There's also another kind of trick that can help some students with the negative charges. Your total charge on each side has to be the same. So if you look at A, B, and C, you started out neutral with no charge. And if you look at the products, you end up neutral, a negative and a positive. Here, we start out with a -2, and we end up with a -1, -1. So the charges do balance. It's going to be something we actually do in a couple of weeks with balancing. All right, this was my base. So the HPO4 becoming the dihydrogen phosphate. The dihydrogen phosphate is now a conjugate acid, and the I- is a conjugate base. Now, what I did not show in this question, and it's going to happen on the next one, but to do E, I have to actually teach you something else, which comes up in 2 pages. But on the study set, if you run into a question with the sodium, just cross the sodiums out. The sodiums don't have any effect on this. And then when you cross the sodium out, that's going to get a negative charge because the sodium's gone. So that's what I did here. I just eliminated the sodiums. It's kind of like what's going on in all of these. We're just ignoring the other ions because they're spectator ions. They don't have any effect on the pH and what's going on here. And so like here, you could cross that sodium off, and that would be HCO3 negative. So some students like to have the sodium on there. The sodium's going to switch places with the hydrogen ion when things move around, or you just cross the sodium out and put a charge on there. All right, we have one more step. The rest of this page we'll talk about tomorrow, but we have one more step with these. And that is, so you label your acid base, they donate a hydrogen, and they become, the products are the conjugate acid, conjugate base, right? So that part is really not too bad. This next step is a piece that takes a little bit of finessing. You're going to be asked which direction is favored. And right now we're going to be doing it without any K values. So A and D are really easy to answer because they're one-way reactions. So if they're one-way reactions, they're going one way. If they're two-way reactions, the rule is, and we'll refine this tomorrow, you always go from stronger to weaker. It makes sense. The stronger wants to donate. The stronger wants to react. So for A and D, if we see a strong acid, end of story. It was one way, we're done. So I usually teach this as like, there's 3 steps you go through. So look for strong acids. So that was like example A and D. If you don't see a strong acid, then you do step 2. What is considered the next step is, look for hydronium or hydroxide. Hydronium and hydroxide are the cusp between strong acids and weak acids. So they're that dividing line. So if you don't see a strong, the next thing you look for is hydronium hydroxide. So here we have a 2-way reaction and you have hydronium. These guys are stronger than any of the weaks, and you're always going stronger to weaker. So it favors the reverse. So you would just put a second arrow that it's going to favor the reverse. So basically it's always going to favor going away from the hydronium or hydroxide unless you see a strong acid, because the strongs always win. Step 3 we're going to do tomorrow is we're going to look at KAs. So we have to learn what KA is to be able to do that step, and that's why we're going to do E tomorrow. Any questions? All right. So, page 13. So the pH scale. We're going to talk about pH. We're going to do calculations. So get your calculator out. And the good news, this tends to be, most students do really well with this acid-base stuff. It's also that kick in the butt to get us going again the first 2 days of the term. And so those of you who did summer school for the first half of the summer were ready for going. Those of us who took like a 6-week hiatus, it was tough for me to get going, but yeah. All right, we're in gear now. So this is the question I always ask. The autoionization of water. What if you had this reaction? H2O plus H2O. What's the acid and what's the base? Well, the water's the acid and the water's the base. Doesn't really matter, but one of them, it's not a strong acid or a strong base. They're very weak. So it's a 2-way reaction. In every cup of water that you have, this is happening. And so you end up with hydronium plus hydroxide. So water, there's always a little bit of water giving up a hydrogen and a little bit of water donating a hydrogen, right? So we get hydronium and hydroxide. It's a 2-way reaction. This actually gets a special K value. It's called KW. Anybody want to guess what the W stands for? Water. And H2O is a liquid. And what we learned about Ks when we write our K formula is we ignore the waters, the liquids. So KW equals hydronium times hydroxide. This is like a long-winded way to get to what pH is. And this is where it comes from. So this is going to be our first formula. So Kw is equal to, I guess I better write it this way first, 1 times 10 to the negative 14. Or you can just say 10 to the negative 14. You can also say 1 capital E negative 14. It really is how you use it in your calculator. And most of you hopefully are fine with your calculators. So this is the first piece. We need this. A quick comment that is going to keep showing up this term. This is at 25 degrees Celsius. I do not know who declared this, but somebody declared that all the K values, because at the end, if you printed your notes, you have 2 pages of charts at the end. And if you look at those pages, there's a whole bunch of K values. Those are all at 25 degrees Celsius. All right. Anyway, that's just somebody declared it. That becomes important in a couple of weeks because standard temperature is no longer going to be, when you did gas laws, remember what standard temperature was? A really cold day, 0 degrees. Somebody decided to have a really warm day, 25 degrees. All right. Your body, by the way, is not standard. That our body's at 37 degrees, although Americans have a crappy diet, so they've changed what standard temperature of the body is in America to 36 or 36.5 as normal, because most people have destroyed their thyroid enough. But your body regenerates itself, so inspire yourself. What this means is if you know the hydronium, you can always find the hydroxide using this formula. So you're going to always get really small numbers. This number is extremely small. This means it's very much reactant favored. Very little ionizes. Very little of the water has dissociated. Very, very, very little. So there's just a little bit of these ions. If you have more hydronium, if the hydronium is greater than the hydroxide, then you're an acid. If you have the opposite, then you're a base. If they're equal, you're neutral. So only if they're exactly the same are you at a neutral. And so going through these, you can see we get these crazy small numbers for our answers as we're going to do the math. And so there's a gentleman who came up with the pH scale. And so the pH scale, most of you have heard of pH, is he basically just said, let's take a log base 10. By the way, this is really cool. This is more for those of you into the esoteric and reality. Base 10 makes no sense. The metric system is like this convenient thing, but base 12 is like what we're moving towards because everything is actually multiples of 12 when you go into the natural world. You can ponder that. So things happen in 3, 4s, or 12s or something. Anyway, except our fingers and toes. So that's the LOG key. When you took 222, we did a lot with natural logs. We're doing logs now. So the other big famous log scale is, of course, the earthquake scale. So the negative log of hydronium is what pH is. In any other class that you learn this in, you will learn it as negative log of hydrogen equals the pH. I just want to remind you, and here we're going to say it this way, because it turns out you can't have a hydrogen ion because the water was what pulled it off. So the hydrogen ion is never actually there. It's always attached to the water. So it is truly hydronium. All right. So these are our 2 main formulas. I'm going to show one more, which is if we wanted to do the opposite of this formula, if instead of using the log, the opposite of log, it's on your calculators, is 10 to the power. You may or may not remember that from your Math 111 class. So 10 to the negative pH is going to equal your hydronium. That's just undoing the log function. So when do we use each one? Well, this is the negative log one is to solve for pH. So like on question A here, what is the pH? We're going to have to use this, negative log the hydronium equals pH. You're going to be using that so much in the next 2 days, you won't need a note card. But rather than, you know, you guys, you get to use your notes for the exams or the celebrations. I don't care. But you should get to the point where you don't even have to think about pH. If you do all the work, yeah, that you just know these formulas. But make a note card rather than trying to go through all your notes and stuff. Make a note card with these there. So while you're doing your study set, you're like, okay, that's the formula. And by the time you get done, this formula here that I just did where I flipped the equation, this is if you're given pH. So if you look down here on B, sorry. So I tell you the pH of P's are. So if you're given the pH, then we take it out of pH and we go to this. And our first formula up here, this is works with hydroxide. So given or to solve for hydroxide. And so let's go ahead and do A and B, and then I'm going to throw another thought at you that you can use if you like, and then we'll work with some K values. All right. So this one, this is all formula based. So a comment for you is always state your formula. Let's say it here. We're not doing factor label this term. We will be at some point, like little bits and pieces. So you're going to always state your formula, like when we did gas laws. Your teacher here is a stickler for this. These are brackets. So the other quick comment is this is molarity. Just, you can't see that. That's from yesterday and the day before. So those brackets, we're dealing with concentration of ions is molarity. So state the formula. And then the other piece that we should point out is this little statement I made here. Strong acids, so SA, is your hydronium concentration. So here, HCl is a strong acid. So really, this is my hydronium. I gave you the hydronium. So if you have this amount of hydronium, what's the pH, what's the hydroxide? So we state our formulas. And so I'm going to give you guys like 2 minutes to try it. So state your formula and solve and see if you get my numbers. And then here, if you're given the pH, state your formula and see if you can get to the hydronium is the first one and the hydroxide. And then I'll show you some more formulas to do these. Or you can take a 2-minute break. If you're watching at home, pause me and just try it. See if you get my answers. All right, I'm back. So, and if you're getting it, just keep going. But how you're going to show your work is, I want to know what is the pH. So you would state your formula. So pH equals the negative log of hydronium. Just real quick, I don't care if you state it how I did here, where you write pH first or last, but you state your formula, and then you would just say, so the pH equals the negative log of the 0.05. This has to be molarity that we're plugging in, and you should get 1.30. We're going to talk about sig figs. So sig fig rules actually change when you do a log function. This answer has 2 sig figs. So I actually obeyed the rules for sig figs since what I gave you only has 2. When you do a function, so logs, natural logs, stuff like that, sines, the sig figs are how many digits are after the decimal point. So for those who want to know all the sig fig rules, there you go. You can go also with the rule I mentioned the first day for this term and just always give me 3 sig figs, and that will be wonderful. There there's a point where I change that, and that's once we get to buffers. All right, what is the hydroxide? So for the hydroxide, we would just do the 10 to negative 14 equals the hydronium times the hydroxide. And so we'd have 10 to negative, so state the formula divided by the 0.050 equals our hydroxide. And that's where I got that number. You can show it with the capital E or times 10 to the power. And again, if you like 3 sig figs, you can do that. All right, for the P's question. So given the pH, 10 to negative pH will give us our hydronium. So there are 2 answers I accept on this one. So 10 to negative 3.65, that is your hydronium answer. So there's always like 2 of you who are going to give me the answer like that. And that's actually how I do it. That is actually a better answer than punching it in your calculator, because this is always going to be an approximate, but you can also give me that as the answer. So more for those of you who have no problem writing a number like that, because this just means we're not doing an estimate. And so that's wonderful. And then 10 to negative 14 for our second step will equal the hydronium times the hydroxide. And this number then will get put in for the hydronium, and we'll get the hydroxide number. There's another way to do this one, and that takes us to C and D. So I'm going to show you 2 more formulas that you may or may not see me use and that you can use. But is there any questions? If you did this on your calculator and you do not get the same answer as me, you're not getting the same exponent, please stay after, come to office hours, just be patient. I stay after usually for at least a half hour, 45 minutes, come back at 5 o'clock from 5 to 6. And right, it will take me usually 1 minute. This is the part that's hard online. But in class, I would have during those 2 minutes gone around to every single one of you to make sure you know how to use your calculator. You have to get these numbers. We do so much with pH for the next 2 weeks. And so it's pretty much half of the class. All right. If you get the hydroxide, this one, if you did it and you got 11.40, it is because this one has an extra step. And so I have this one here on purpose. That capital M is moles per liter, just to remind you, of barium hydroxide. When we're dealing with hydroxides, you do have to factor in how many hydroxides. So for every 1 mole of barium hydroxide, there are 2 moles of hydroxide. That's the subscript, the 2. So my hydroxide is double that number, 0.0050 molarity. That's my hydroxide. From there, you can find the hydronium, and from the hydronium, you can find the pH. So you can also go vice versa. If you're given the pH, you can change the pH to the hydronium, and then you can change the hydronium to the hydroxide. And then I think there's one on the study set where then you have to work back to actually go all the way to grams. So, right, if we have grams, you could actually go, right, change grams to moles. I just remember doing that back in your first term of chemistry. I want to show you 2 more formulas here. And so that's why my answer, if you didn't double that number, you'd get like, I think 11.4. That is not close enough. pH is a logarithmic scale. Changes here, this is really important. So one of the things I did say 3 sig figs you could always go with. pHs, I asked that you show pHs to 2 decimal places because the decimal place does matter for pH. A small change in pH is actually significant. I talked about that, about acidosis and stuff, which we talk about more next week when we do buffers. All right, there is a scale. When I was in school many moons ago, I had never heard of this scale. actually, when Major was in my class, I mentioned, I said, has anybody ever heard of the POH scale? And half the class raised their hand. And I was like, are you serious? Nobody uses the POH scale except high school teachers. And so they just made it up because, but what this little p means, whenever you see a p, that little p in front of something, that means you're doing a negative log. That was the guy, I can't remember his name right now, but famous chemist. I talked about him in that one video that you haven't posted yet, but that's where pH, it means negative log of the hydrogen ion, hydronium. So POH or poo is the negative log of the hydroxide. So 10 to the negative of any P, so 10 to the negative poo, would give you the hydroxide. I mentioned this because there's actually a really nifty trick. And for those of you really good with math, you may have already noticed this. If we have this formula from up above, that the hydronium times the hydroxide equals 10 to the negative 14. If you logged this whole thing, you would get, right, if you log it, when you're multiplying something, it becomes adding the two things, and it gets rid of this 10 to the power, basically, and this is a negative. It's a negative log with pH also, because of the negative exponent. So that's why this is not minus. That would be one of the things on your calculators. It's not the minus sign. It's not minus log. It's the negative button. So just be careful with that. That's something that some people get stuck on, and they're like, oh, of course. And don't worry. Don't be embarrassed. It's sometimes simple things like that. But this is a handy dandy formula that the pH plus the POH for a solution is going to always equal the number 14. So you can play with this. This is actually very useful. But if you know the POH, this is a scale of basicity, of how basic something is. Nobody talks about the POH scale unless they're trying to see if you understand logs and stuff. So we're going to usually be talking about the pH scale, although you might run into questions with POH. So with that, before we move on, just kind of a big picture, which we'll go through more tomorrow. Let's write it up here. As you increase the hydronium, you increase the acidity. The more hydronium, the more acidic something is. What that means is you lower the pH. So actually way back to when I asked, what do you think of with acid base? And Major said below 7 pH. The lower the pH, the more acidic something is, which means these are always opposite. As the acidity goes up, the pH drops, and that is because of that negative sign there. So let's see if somebody gets it with the POH scale. POH, actually, let's go back up here, one more. If we're talking about the pH scale, as you increase the pH, it's going to become more alkaline or more basic, which means you're going to decrease the hydronium and increase the hydroxide. Actually, I'm going to leave it like that. You can ponder those because there are going to be questions that we'll do tomorrow. We'll say which one has more hydronium, and you're not going to be doing any math. You're just going to be thinking about it logically. So the stronger the acid, the lower the pH. The stronger the base, the higher the pH. All right. And it is pronounced pH. You actually say both letters. This is a true story. I had in graduate school a guy who it was a salesman came in and they're like, oh, you have to talk to Joyce. I was like a 25, like you guys, 24, 25. And so I'm like, I'm in the middle of experiments. Just give me like 2 minutes. But it's like a young guy and he sees a young girl. So he has to like make small talk, even though I'm busy and saying, just shut up. And so I'm ignoring him. And there's a pH meter next to me. And he goes, this is a really nice meter. And like everybody in the lab just stopped, including me. And I turned to him and I'm like, and he just starts sighing. And then I had a 15-minute conversation with him about my meter. And needless to say, nobody ever bought anything from this guy. So even if you don't go on to become a dentist or something, you should at least know it is not pronounced, it's pronounced pH. I honestly don't care if you call this POH or poo, because nobody uses that scale except for doing math in a class like this. All right, we're going to do one more. We're going to do 2 more problems because they're on your study set for tomorrow. The good news is it's actually, we get into pH, people tend to do much better. Your worksheet for tomorrow night is actually, might be the easiest one the whole time. So you're going to be fine. You're now in the mode. All right. So strong acids completely ionized. Back to this comment. Strong acids, you just plug right in. Hydroxides, figure out how much hydroxide, we plug it right in. Weak acid, they're going to be K formulas. They were equilibrium. They were 2-way reactions. So we have to have a K value. The A stands for acid. KB stands for base. I'm going to write some stuff out. You can just kind of listen or you can write it out. But they usually write an acid, as HA. This is my weak acid, plus water. And so water would be the base. And this is going to donate its hydrogen. So HA is just generic. It's a generic acid. It's a weak acid. It's a 2-way reaction. And so what you're going to end up with, the H2O is going to become hydronium, and the weak acid is going to become, they will write it as A negative, which is its conjugate base. So if we write the K expression, students never like the ha. There's a whole form of Qigong and yoga called ha. And all you do is go ha, 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 until you're laughing and giggling and jiggling, and it's really good for you. And it's really nice to see. Like, I can see the students who've had me before. It's because they keep their cameras on. All right. I just wish I could see the whole class, because then we'd play the game. You guys did it like at summer camp, right? And you lay down on each other's belly and you had to go ha, 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 and you feel the other person's belly. And once you get up to, anyway, it's really fun. We didn't play that game, but we would just say ha. So products, hydronium times conjugate base. Over reactants, we ignore the water. So that is our Ka formula. The last 2 pages have a whole bunch of Ka values. We're going to talk about these pages tomorrow. I usually give you the Ka value within the question, because Ka values are approximates. And if you Google a Ka value, you'll get a slightly different answer than me. And then all of your answers will be different than me. And because then you're going to do a log on it. A log function will change a small difference when you do a log will make a bigger difference. And so we're going to use those charts that are in the notes or the ones that are in the problems. So this is the Ka. We're going to do one other one, which is, it's a ratio of acid to conjugate bases, or conjugate base to acid. But this formula, this is how I solve it. And we plug in, and let's go ahead and do this one. There is an assumption we make, and I'll get to that in a minute. We're not going to have to write the reaction out. We just see, you're going to know it's a weak acid because it's not one of the strongs, and you're going to see a Ka value given. So you're going to say, okay, I'm going to write my formula. Ka equals hydronium times the conjugate base over, and you can say wa, or you can just say acid, or you can just say A. That's kind of up to you. Some people like the wa, some people just say A. So this is the good news. And some of you will believe me, and some of you will decide that Khan Academy does it much more professionally, and you'll want to write your chemical equation, and you'll want to do your ice chart, and you'll want to do your plus and minus X. You don't have to do that here. I'm going to do it. Don't write this down. Just listen. So normally what we did, like yesterday or today for your study set, you did HF plus H2O, and we went to F negative plus H3O, right? We would do our ice chart. Again, don't write this down. Just listen. And the HF was 0.15. These are 0. We ignore the water. And we say minus X plus X plus X. So we say, okay, this is 0.15 minus X. Always a piece some of you are missing on the other stuff. We're not going to do it this way, though. And then you would plug in, and you'd have an X squared, and you'd have a 0.15 minus X, and you'd be like, oh my God, we have quadratics. There's a huge step you get to make with this, and we don't have to do any of this. And it doesn't make sense here. This is how it's like always written. But Ka values tend to be really small. Like this is a pretty large one, but they always have negative exponents. What that means, because the K value is really small, X is really small, like really, really small. The change is so small that this is not going to change. So we just ignore it, the minus X. So basically what we end up with is just X squared over 0.15. We just make the assumption that these two are going to be the same, and the acid is whatever we started with, and it's just an X squared problem. And so we don't have to go through writing the equation, writing the ice chart, plugging all that stuff in. Now, with that, so you can go through, you would solve for X, and I'm going to babble while you guys are trying this. X is going to equal both of these because they were the two products. We have equal amounts of them. But I don't care about the conjugate base. I'm trying to find the pH. So what I want is X is my hydronium. So right, you're going to move the 0.15 over and then take a square root. Then, so that's step 1. Step 2 is you're going to do negative log of the X, and that will give you your pH, which hopefully you get is 1.98. So while you're trying that, I have to tell you all something, but I have to find where I wrote the note to myself. Or you can just make a note and try it later. But again, you don't have to do ice charts with weak acids. We will after the midterm, but for study set 3 and study set 4, worksheet 3 and worksheet 4, you can ignore it. There's always somebody who doesn't believe me, but I know what it is. So this is a quick comment for you all. It is a typo. I had fixed the typo and then I posted the wrong worksheet. So if you've done the worksheet, I actually, this is the study set. I forgot to give you answers on that study set, but on the worksheet, on worksheet 2, question number 4 is, it does come out as a quadratic. If you have the solve function, which like more than half of you have, it's great. You can just solve it. If you're like really geeky in math and you love doing quadratics, you can just solve it. That's fine. If you're like, oh my God, really? You're going to make me do 2 quadratics? You have to change question 4 and you have to make both reactants. Sorry. And I have the answer both ways. And I apologize. I fixed my typo and then I posted like with the typo. So you have to make both reactants 0 point, I can't remember now. There it is. 0.4444 ATMs. Their pressures are almost the same, but I changed the one and forgot to change the other one. And so it actually almost comes out the same, but if you just make them both 0.44444, then you don't have to deal with quadratic. So if you're somebody who's like, I don't want to deal with quadratics, we'll do it that way. And I did all my practice to try before I posted it, and I didn't even notice that typo, so I apologize. So that's on the worksheet. The study set will go over at 6 o'clock, and I'm just looking again on the study set that you make an effort, that you make a good effort, not that you like write one little thing and then put a big question mark. Then you'll get a 4 because you'll turn it in after I go over it. All right, so questions. This is how we deal with weak acids. Again, you don't need to go through an ice chart. You don't have to do any of that stuff. The percent ionization. Is, sorry, I have to think. It's been a year since I did it. It's a change over the initial equals the percent. So if you remember yesterday, we did, it shows up on the worksheet, the very first question on the worksheet, and I think one of the questions on the study set, initial times percent equals change. We're just rearranging that. So the change is your X. So whatever you get for X over the initial amount, the 0.15, that is going to give you the percent. And you multiply by 100 to make it a percent. That's so that's where this comes from. And it's a terrible question because it's saying ionization. It should say percent. Let's change it. It should say percent dissociation. Anybody know why? I've mentioned it like 3 times. Acids don't actually ionize. They need something to pull the hydrogen off. So the bond with the hydrogen is actually a covalent bond. And so they need somebody to pull the hydrogen off. It's just an extremely polar covalent bond. And so it's really easy to pull that hydrogen off. So it's how much of it. And this is actually quite a bit, 7%. It's usually really small. I can see the answer here, 2.7 or 0.0088. We're going to do one more problem, and that's because I looked at your study set and there is a question about a base, and I just want to show you how to do it. We're going to do the same assumption. We're not going to worry about doing ice charts with these. On C, we'll do C and D tomorrow, but these are, you just start with mass. And so you just change it to molarity to be able to use it. The difference is, why I want to show you how to do B is it works with a KB. And so if you have a base, we're going to use this formula tomorrow. You can't do that here. If it's a base, so if it's an acid, you use Ka. If it's a base, you use Kb. And so if Ka is this formula, Kb is the exact opposite. So instead of hydronium, what ion are we going to write?
Hydroxide.
Yeah, it starts with the O, ends with the H. Instead of conjugate base, we're going to say conjugate acid. And then on the bottom, you would just say either weak base or base. I don't care how you say it. So NH3 is a base, so it's the same idea. We would plug in, state your formula, and then you would have your 1.8 e to the -5 equals, these are x squared problems. The 2 on top are the same. We have x squared over our 0.025. Now, this is something I'm going to keep emphasizing today, tomorrow, all next week. Whenever you solve for x, always tell me which ion it is. If you're dealing with Ka, your X is your hydronium. If you're working with Kb, your X is your hydroxide. I can't emphasize that enough. That is one of the biggest mistakes. The students who are like, I don't have to do that. They're going to mess it up because they're going to just always go right into pH. And that's not going to work here because if you take negative log of X, you're not going to get the pH. You're going to get what? You're going to get poo, right? You're going to get the POH. And then you can just do the trick of the pH plus the POH equals 14. So basically 14 minus the POH. One other thing that I want to mention, because I just thought of it, the pH scale. Most people think of the pH scale as going from 1 to 14. That is actually not true. You can have a negative pH. If you had a negative pH, what would that mean? I'll let you ponder that. You can email me if you figure it out and tell me when that could happen. You could also have a pH higher than 14. So what would that mean? And so any questions before I stop?
Sorry, I have a quick question just out of curiosity. Why do we have to use molarity if we're not going to use units at all?
Why do we have to use molarity if we're not going to
Use units. Like if the units are not included at all.
No, the reason I'm not showing the units is because they have to be molarity. So these don't deal with gases. So Ka and Kb, Ka stands for acid, Kb stands for base. They are assuming everything is molarity. pH, all these formulas that I dealt with today, these all assume molarity, that you're in molarity. Where that becomes important, Major, is like here where I give you grams and volume. You have to take this and change it to moles per liter. To be able to use any of these formulas, these brackets mean everything's molarity. And so it absolutely matters. The formulas don't work unless you're at molarity. Awesome question. So thank you for asking that and to emphasize that. We're not dealing with gases, so all that stuff that we did with KPs and ATMs, that's why I said the acids and bases in some ways are a lot easier. And also we're not going to deal with ice charts because weak acids and weak bases, they ionize so little. Like this is a lot. It's usually really small, less than 1%, that the change is not significant enough. We will come back to the ice charts next week in the third week. So don't worry, we learned them for a reason, but we can just ignore them. And these become X squared problems. So everything we're doing today and tomorrow with the weeks are going to be X squared, which is great news. That's how everybody ends up thinking of them as X squared. Biggest point also is with the acid base stuff, you have to state the formula you're using when you use it. So you state the formula, you show what you plugged in, you give your answer, and then you keep going. All right, anybody else have a question? And again, I'll be back at 6 to go through your study set.